Welcome to Sikkoville, a small town in the Netherlands where the weather is nice, the grass is green, and the people are friendly. There is, however, one big problem in Sikkoville. Every year an influenza virus comes and infects hundreds of people. Because the infected can't go to work, the economy suffers. A lot. With the costs of a single infection at €1,000, the epidemic costs our peaceful little town around €1 million each year. The mayor of Sikkoville has seen this process happen for quite some years now, and she wants to do something about it. She thinks she has found a solution. Next time the epidemic comes around, she will make everyone in the town wear mouth masks to prevent the disease from spreading. It seems like a good plan, but will it work? Buying and distributing the mouth mask is quite a lot of work and will cost a lot of money. So will it be worth it? Desperate for a solution, the mayor turns to the Technical University for Delft for a solution. And this is where we come in. With the help of the AP model package in R, we are able to simulate an epidemic and investigate how certain policies would affect the spread of the disease. It works as follows. The population of Sikkoville is represented by a graph in which the people are nodes. These nodes can be in three states: susceptible to the disease, infected, and recovered. The connections between the nodes represent the relations between inhabitants via which the disease can spread. A random process generates a graph that changes over time, and this gives us the virtual population on which we can experiment. All that's left to do is specify the initial amount of susceptible, infected, and recovered nodes, and some other disease parameters like the probability that an infected node infects a susceptible node it is connected to, and we can let the program run to simulate the epidemic. Now we can start to investigate whether the mouth mask policy should be implemented. A single mouth mask costs 20 cents. And per inhabitant, about 50 are needed if everyone is to wear one every day of the entire duration of the epidemic, bringing the costs per person up to €10. Distribution costs should also be factored in and are estimated to be about €5 per person. For our population of 5,000, this means that the total costs of the mouth mask policy are €75,000. This means that if the policy can reduce the number of infected by 75, the policy is profitable. Now, if the disease is left unchecked, it will infect anywhere from 13 to 4,000 people, but on average the final number of people that had the flu is about 1,400, which means the total costs would be €1.4 million. To simulate the effect of mouth masks, we simply take the values of the unchecked epidemic at the time step on which we enforce the policy and change one parameter, the infection probability. Mouth masks reduce the amount of viral particles that spread by a factor of 3.8, so dividing the infection probability by 3 seems about right. We speak of an epidemic if for 5 weeks in a row more than 5 people per 10,000 visit the doctor, so the minimal time at which we can have an epidemic is 35 days or equivalently 35 time steps. Taking the number of infected and recovered at this time step and rerunning the program with a reduced probability of infection gives us, at the end of the simulation, about 800 people that at some point had the flu, which is 500 less than we had originally. The costs with the addition of the mouth cap policy in place are at a total about €900,000. Our conclusion is that mouth caps could potentially save up to €500,000. The mayor of Sikkoville is happy with our results and decides to order 250,000 mouth caps. The next time the influenza virus comes around, far less people get infected. The only thing she's left wondering about is what could have been if the policy could have been enforced more quickly after the first infections take place.